also going to share my screen and we will start. I and the students are here. We're ready to go. And I'm showing you a screen. Can everybody see this screen?
Yes.
Yes.
Excellent. All right. Yeah.
Yes. You can.
I'm just going to put this right like this. And so we're going to start. This is a project with Tennessee volunteers. We're looking at the experimental test stand to formulate guidelines for the injection and thorough mixing of air ions in HVAC commercial air handling units. Next slide. Myself as an advisor, Dr. James Friels, who was worked at Oak Ridge National Laboratory as I did. He was a nuclear engineer, and he's an expert with the use of COMSOL. We used COMSOL to try and model the flow of ducts, and I attribute most of the success there to Dr. Friels. Gary Bergeron, who's principal and co-owner of Kelso Regions, was also one of our advisors. My students, Omar, Christian, Stephen, Joseph, and Joshua. Each one will give a presentation today. I'm just going to lead out in terms of an introduction. So air ionization, it is a way of filtering and disinfecting airborne microorganisms. Indoor air quality techniques are listed here in terms of order of decreasing efficacy, and bipolar and needlepoint are right at the top. What's the advantages of air ionization? Well, both of those techniques, they use low energy. They're very effective against bacteria, viruses, mold, fungi, whether in the air or on the surfaces. They can neutralize particulates such as volatile organic carbons. They eliminate unpleasant odors. They will even eliminate static electricity, and they produce no chemical or harmful byproducts. There's no ozone production techniques. So it is a very useful system. So in terms of air ionization, in terms of air cleaning technologies, there are various peer-reviewed studies that I show here. There are links that you can go to these and look at them in terms of decrease in bacteria deposition and the ability to inactivate airborne bacteria, the ability to remove airborne particulates, and also to increase submicron particulate deposition to surfaces. Best practice. Where is the best place to inject these air ions? The team, myself, we felt that the best place to do this is on the supply side of the HVAC system of the air handler unit itself, not on the return, because in the return, the air is going into a wet coil. The ions would basically clean the coil, but they would be rendered used by the time we would want to use them for killing any type of or sterilizing the air. So we felt the upstream or downstream side of the air handler unit on the supply was the best place. So the knowledge base that we're looking to try and develop is to formulate guidelines for injecting and thoroughly mixing air ions in highly turbulent airflows. You'll understand just how turbulent these flows are for some of the air handler units that we have on campus. That will be shown. The implementation, to do that, we want to implement air blenders. Air Blender Products has a product that you're seeing to the right here, and we're going to do correlations for pressure drop. We're going to try and develop equivalent lengths for mixing. How far downstream will the mixing go in from a rotational flow to more of a turbulent bulk flow? And we have some flow visualization that we're going to conduct. These are turbulent flows that we're talking about. And I pulled this out of a white, it's a textbook showing in the Y is, think of that, is going into the radius of the tube. Center of the tube is the dashed line. And I'm showing the shear forces as well as the velocity. And in a turbulent flow, you have an inner layer that's at the wall where viscous shear dominates. In the outer layer, towards the center of the duct, circular duct, you have turbulent shear dominating. And in the overlap region, which is hard to model and is based primarily on experimental data, you have both viscous and turbulent shear that work together, and they're both important in that layer. Now, our concern is when we look at this model, and we know that there's turbulence going on, and so there's mixing going on. But is there mixing that's going through the complete bulk of the cross-section of the duct? And here's just a simple duct system, a flow visualization that was done. This is not at the inlet. This is after several equivalent diameters downstream of the inlet. And what you can see is the turbulence here at this section, but you can see around it, there is some eddy currents going on, but to really make it where we get intimate contact between the air and the respective air ions, we felt that the use of a blender might be very useful for slinging the outer perimeter air into the core and slinging the core to the outer air to get a good mixing effect. So that sort of basically describes what we're trying to accomplish. We have an HVAC duct system set up. I'm going to allow the students to now speak to each of their sections, and we'll start.
Hi, my name is Christian Isaacs, and I'm a senior mechanical engineering major here at the University of Tennessee, and I'm going to go over the approach and objectives of this project. We can go to the next slide. Yeah, so we as the students, we investigated the building and HVAC duct system for the purpose of acquiring data. We then sized the same HVAC for airflow rates in the transitional range of turbulent to fully turbulent. We then used a blender in the HVAC for mixing air ions in the majority or bulk of the airflow. And we measured the pressure drop across the blender and across the entire HVAC duct so as to make correlations, like ion generator placement and stuff of that sort. There's also a concern with rotational flow. And let's go to the next slide. So a proposal was submitted to the University of Tennessee Office of Sustainability with the title of The Effective Mixing of Air Ions with the Supply Air from Large-Scale Air Handler Units for the purpose of neutralizing SARS. So we were awarded $60,000 in funding, which we thank the Green Space Association for. And we used that funding to set up a test stand for setting guidelines for the best positioning of air ion generators for the maximum amount of mixing of ions with other molecules. This helped us to achieve or get closer to our end goal of making a more sustainable campus by retrofitting existing campus HVAC systems. So we go on to the next slide. So on your screen, you'll see a pie chart showing the electricity consumption of commercial buildings in the year 2012. Of course, there's a lot of energy as used for lighting, but the two things that I want you to take most note of is the cost associated with ventilation and cooling. So currently, in order to ventilate air and a clean air, you have to take outside air in, which helps dilute the inside air and makes it cleaner. This is the most pretty much common way of cleaning air inside. Associated with that is a cost of cooling. So say you're on a hot summer day, it's 90 degrees outside or over 90 degrees outside, and inside you want it to be around 70-some degrees. There's a lot of costs associated with cooling that air down. So currently the most common way of cleaning air, there's a good portion of money spent on this whole ventilation and cooling system. So we'll move on to the next slide. So with bipolar ionization, there is a lot of benefits that are associated with the 3 pillars of sustainability, those being the economic, environmental, and social benefits. So for economic, there are benefits associated with breaking down the volatile organic compounds. It eliminates unpleasant odors, set of electricity, and many things of that sort. Most notably, kind of referencing our previous slide, it reduces the cost associated with ventilating air. And there's many examples underneath there that you can read. There's also a lot of benefits associated for the environment, such as a reduction in CO2 emissions and other carbon compounds. There is also a reduction in outside air intake, which reduces the amount of electricity demand. There actually is a lot of social benefits as well, such as the sterilization of bacteria, viruses, mold, and most notably SARS, which was found that after 3.3 seconds of ion exposure, about 73.4% of a active SARS pathogen population became inactive. So there's been some research done on that. I'd like to now give the presentation over to Joshua Leone, who's going to talk about ion generation.
Good morning, my name is Joshua Leone, and I'm also a mechanical engineering senior at the University of Tennessee in this regard. So I'm going to be discussing the ion generation and its applications for killing airborne pathogens, such as the SARS and influenza and other airborne pathogens. So first I'm going to discuss the evidence of airborne pathogens being thread to multiple individuals through the HVAC systems. So back in the beginning of the pandemic in early January 2020, not very much was known of COVID or what kind of impact it would have around the world. So an article published by the CDC examined a family that visited Wuhan, China at the beginning of the pandemic, and then later returned to what I don't know how to pronounce this China's city name.
Wuhan?
No, Gusan. So
Okay.
Guangzhou. So they went to Wuhan and then they came back to their home city, and that family ate at a restaurant, and they ended up infecting two other families that were sitting across the restaurant. So they were further than 6 feet. They were shown in the picture. They were pretty much all the way across the restaurant, and they were still infected. So the culprit of this extended distance of transmission of the virus was determined to be the AC airflow patterns. So since we're unable to shut down the HVAC systems purely on the grounds of it having a negative impact on the transmission of airborne pathogens, a solution must be proposed to help prevent the spread of sickness in any and all indoor spaces. The solution Dr. Miller and my team are investigating is to inject the air ions into the HVAC airstream. And so the way air ions help to kill the airborne pathogen is by injecting positively and negatively charged ions, and they attach themselves to the outside of the pathogen's membrane. It begins to break down the virus proteins, which cause the pathogens to become inactive, leaving it unharmful. So there are several key features we need to analyze in the air ions in the application of killing the pathogens. The two main areas of focus would be the contact time the air ions have with the pathogen and the concentration of air ions in the airstream. So there was a study done that shows that air ions are able to destroy 99.7% of the coronavirus contaminants in 30 to 40 minutes in a stagnant environment. Obviously, that's not really practical in an air duct and heating and cooling a building because the circulation is much quicker than that. So the way we propose to solve that issue is by making sure there's a good mixing in the air duct so there's good contact with all the pathogens and viruses, anything that we're trying to eliminate, so that most of the air ions aren't like clumping together, or they get good contact and engage the membrane of the viruses. So we determined that with the mixing, there was a significant decrease in the time it takes to destroy the harmful viruses. And with some of our investigation, we did console, which Omar will discuss our findings in.
Okay, so my name is Omar Al-Kai, and I'm also a mechanical engineering senior at the University of Tennessee, Knoxville, and I'll be discussing our results through computational fluid dynamics using CompSol throughout the year. So our goals and our deliverables, we wanted to simulate airflow within an isolation room in a hospital. We wanted to use those results to enhance ion generator usage and show effective mixing, and our goal is to use data to optimize the structure of a room without changing existing HVAC. The point is, we want to create a design that can be retrofit into already existing HVAC systems so that it's easy to implement and will obviously be effective. So to begin with console, we wanted to start with a concept check, something that would we could kind of compare to previous knowledge. So we decided to do a 2D conduction heat transfer problem using various nodes. We did it across 3 different mesh sizes. So we initially coded a solution towards that in MATLAB, which is shown in the top left. And then we used console to mimic those conditions where we have 3 insulated layers on the left, right, and bottom, and heat only coming in from the top layer. And we used COMSOL to solve for the thermal conditions, or the thermal boundary layer. And you can see an almost identical result when going across. This is a 1D plot, so it's only plotted against the x-axis. But we saw almost identical results to solving it in MATLAB, which gave us kind of a intuitive understanding and helped us understand how COMSOL worked. And once we had that under our belt, we kind of went on to the next stage, which for us was to model a simple room with a single intake and exhaust duct. So that simple room was just a cube, and there was 1 inlet and 1 outlet duct. It was run at very low velocity, so there was laminar streamlines present, and we also looked at the actual duct itself to determine the velocity layers. You can see that there's increased velocity towards the middle of the duct as you go in radially, and slower velocity due to viscous effects as you get closer to the wall of the duct. And so with all of that knowledge kind of under our belt and all that experience, we went on to model our actual test stand, which is approximately 15 feet long at a 16-inch diameter. Initially, we attempted to use a K-epsilon turbulence model, which involves 2 transport variables. The first transport variable is the turbulent kinetic energy, which is the K, and the second transport variable was the dissipation, the rate of dissipation of turbulent kinetic energy, which is the epsilon. When we initially did this, we could not get a converging result that was within an order of magnitude of the velocities that we wanted. I think we're getting somewhere like 500 or 600 meters per second. So we ended up using a realizable K epsilon turbulent model, which is similar to the K epsilon, but it treats the turbulent viscosity as a variable rather than a constant. And that has a better ability to demonstrate mean complex flow structures. So what we found was that picture on that top left shows the side from the inlet, where the picture on the top right shows the exit. And we have laminar flow up until we hit our blender, in which there begins to have significant mixing. And we found that there was still effective mixing towards the end of the duct at 15 feet.
My name is Steven Johannesson, and we'll be going over the hardware and implementation of our test system. So this is one example of why we would be installing it. So where we would be installing our design would be a hospital isolation room, which is a second form of contact between the air and the airborne diseases. So we would be looking at installing our ion generator with the blender in the supply side of the isolation room, which would be on the left picture, and on the top on the right picture. So it would work for both examples of an isolation room, and we want to prevent the airborne diseases from spreading throughout the entire building. We want to try to get ahead of them and clean the isolation room and ensure that there's a good mixing of ions and air going into the isolation room. So this is the actual visualization of our test stand. So the entire thing is 15 feet long, and going from the left to the right, not on the picture. So the picture's flipped whenever you're looking at it. But on the left of the top section, we've got our bell mouth all the way on the left to ensure that we get an ample amount of air entering into our system. We have a small section of duct with the first static probe that will be measuring the pressure drop across the entire testing system. So then after that, we've got a laminar flow meter with a honeycomb grid inside of it It's just gonna help straighten out our air. And we've got a hot wire anemometer inside of there that will be measuring different things that we will be talking about in our sensor section. So then after that, we have another section of just plain aluminum duct with a static pressure volume probe inside of it to measure which is going to correlate to this pressure drop across the blender. So after that, we've got two sections of flow visualization acrylic duct that we'll be showing you later, with the blender in the middle of it to ensure that we've got a good mixing of the air and the ions once we start injecting ions in our test stand. So after the blender, we've got the second half of our pressure probes for measuring the pressure drop across the blender. And after that, we've got another section of duct with the final pressure probe inside of it that is going to measure the entire pressure drop across the system. So at the very end, we've got the inline blower, which is the FKD16 inline blower that's capable of producing 2,950 CFM at zero static pressure. And then we've got the exhaust of the air. So we want to thank Blender Products Incorporated for collaborating with us on this project. And during this collaboration, we coordinated with Mark Pavol, the Director of Engineering over at Blender Products Incorporated. So on the right, I've got a picture of the blender, and it's got, you're looking at it, it might look like it spins, but it's actually, those are angled stationary blades that will be ensuring the mixing of the air and the ions once we start injecting ions into our stand. So the purpose of this blender, what we're using it for, is to prevent air stratification, which is just mainly mixing the cold air and the hot air inside of a duct so that there's not discontinuities, which will help ensure ion delivery, but then that also plays into just saving on energy costs and, you know, helping out the environment. So now here we've got actual data for the Hodges library, which we want to go back and install these units into, these air ions and the blenders. So if you look, you've got some of these air handler units are pushing out Reynolds numbers of over 1 million, which is highly, highly turbulent flow. And that's where we want to start out our implementation of our ion delivery system. We want to go ahead and push those into air handler units that are putting out large volumes of air, where we can get a good mixing of our air and ions.
My name is Joseph Gislak, and I'll be talking about sensors and data collection from our experiment. So this is the instrumentation we use to collect data from our system. We equipped our sensor board with 2 Beltron DPT 2500 static pressure probes with the purpose of measuring static pressure across the system, but mainly our blender in units of inches water column. We also had an ElectroFlow G5 thermal airflow transmitter to output the total flow in cubic feet of air per minute, the velocity in air feet per minute, and the temperature in degrees Fahrenheit. Additionally, we used a variable speed controller for our downstream blower, as Lane mentioned, of running our flow up to 2,950 CFM. And all of our sensors were outputting in a range of 0 to 10 volts direct current to our Campbell scientific data library. So we ran a few tests and collected data, and this is what we noticed. Number one, there is a proportional relationship between the pressure drop and the flow rate. So as you can see in the top figure, as our CFM increased, we saw a similar increase in the pressure drop in both the blender and in our total system. Number two, about 80% of our pressure drop actually came from the blender, where the flow became fully developed at about 2,050 CFM. And so what that means is, as the turbulent flow becomes fully developed, viscous effects create fully developed velocity and momentum profiles, which will remain constant. And additionally, the pressure gradient is at a constant value, where the pressure force is being balanced by the viscous forces. And in the future, we plan to develop correlations to evaluate pressure drop and power loss. So as I mentioned in the last slide, about 80% of our pressure drop came from the blender. So we want to know how this affects our power loss. Number two, given the current state of the world, we think that our technology could become particularly useful in hospital isolation rooms to combat things like COVID-19 and improve the overall patient air quality in the room. And we would also like to retrofit our system into the current design in the HVAC system of the Hodge Library. We project this to cost just under $300,000, and we plan to include bacterial, fungal, mold, CO2, VOC, temperature, and humidity sensors. So we'll be talking about the role of relative humidity now. Relative humidity is a key factor in determining how viable a particular virus is. So we understand that research has indicated that viruses die off much quicker in higher relative humidity environments. And in these environments where the viral loads are dying off quicker, there's much less a risk of infection. So as you can see here in this figure, as the relative humidity dips below that 40% threshold, the virus is becoming particularly infectious. So key takeaway there is that drier air makes it much harder to combat viral infections. And lastly, infectious droplets. So in regards to droplets, they shrink, travel far, and evade surface cleaning when the air is drier. So as I just mentioned, drier air makes it much harder to combat viruses. And as our time and distance increases, we can see that the droplet diameter becomes much less.
Okay. We have videos to show now. While I'm getting that video up, would you like to ask a question of the students?
I would. Can you hear me?
Yes.
Okay. So I'm Gary Bowles. I'm with Electric Power Research Institute. Actually, I'm a contractor that's helping them. But my background is nuclear power. So I have some interest in this from the standpoint of keeping the air clean going to the control rooms in nuclear power plants, and it could be other locations also. You mentioned early on that this would be effective against airborne particles, although most of your discussion is about pathogens. Do you think it would be effective in trying to reduce the number of radioactive airborne particles, because that can be a concern in an accident situation?
Gary, it's a good question, and I don't have an answer.
Okay.
What I do know is the mechanism by which it works. The air ion has got an electrical charge to it. And if that radio particle that you're talking about has a neutral charge or a similar charge, maybe there is going to be an attraction between the two. And then the respective cluster would agglomerate to the floor.
I don't know what charge the particle would have. It could be contaminated by beta, and beta has a negative charge. So, you know, that might be something to think about.
Air ion be positive or negative charge.
Well, for radioactive decay, there's normally 4 different types. There's alpha, beta positive, beta negative, and gamma, where alpha is positively charged, beta positive is negatively charged, and beta negative is positively charged. There hasn't been any publishable research on that we know of, or that we've seen at least. But if the mechanism of action holds true, maybe there is some cause or some possible way that could work. But as far as we know, I don't think we've seen any research. But if the mechanism of action holds the same, then it's
Yeah, I don't think alpha would be in the mix here. My thinking is it would primarily be beta. The other thing thought about, one of the things we have to worry about in the plants is chlorine resulting from the breakdown of fluorocarbons like Freon. Would it be effective at all against those type of chemical contaminants?
It has been shown to take and precipitate out volatile organic carbons.
Yeah, I saw that. Okay. And the last one is, the other pathogen I thought of when I saw this is we occasionally see outbreaks of Legionnaire's disease. And I would think this, based on what I see, this would be very effective against that. Is that correct?
I'm going to say a qualified yes to that, yes.
Yeah. And that's not necessarily a problem in power plants, but it's a problem in general,
I have read where it will work against SARS, it'll work against tuberculosis and other style of pathogens. So I wouldn't be surprised that Legionnaires would also be, it'd be effective against it.
I think it's the bacteria. I'm a pretty good engineer, but not much of a biologist. So,
But your questions I like your questions because what that does is it opens up information for future work.
Yeah.
I'm after here. So thank you.
Okay. One quick comment on the nuclear stuff, and again, just it might be a nice coincidence, but what we've seen, right? There's this. I'm sure you're way more familiar with it than I am. The ANSI N13.1. It's actually the specific standard is around duct monitoring. So when you have a single point probe that's monitoring either your discharge from labs or things or into your control rooms, typically that requires you to have a certain amount of mixing, and there's a homogeneity spec there in case you have a pinhole in a filter or something. So what's interesting is that you typically already have in well-designed systems, the necessary mixing's already there a lot of times. So all you would have to do is add the generator in. Again, assuming it's a well-designed system and all that.
typically these systems have charcoal and HEPA filters, but they can be pretty high maintenance.
Yeah.
So this might reduce that. I don't know. Just a thought. That's all I have.
Okay, so with that, I'll go ahead and show this one video that we have. We got a couple of them. We are generating fog, theatrical smoke, and we are looking at it upstream and downstream of the blender. And I think the upstream is to the right, and then downstream is to the left.
Just a brief. So when we were doing the experiments, the fog producer would produce too much smoke to where we couldn't see the interchange very well. So you can see the laminar flow region on the right side and then turbulent on the left, right as the transition of a lot of smoke goes through it. So go back to like the middle. There.
Yes, that's about where it starts.
Yeah.
So you can see the laminar flow.
Yeah. To emphasize here where that laminar flow is, we have the air monitor that's measuring the CFM, and it has a honeycomb grid that's going to force the air to be more laminar, even though it's a turbulent flow range. So you can see these streamlines. It's not streamlined, but that's the flow field that's coming in. And then out on the other side of the left is where it's come through the blender. The lights, those are LED lights. We have LED lights on order that would go to different colors, and they just have not arrived yet. That's the scenario there. So it was quite an ordeal to try and get a smoke that the university would allow us to use in terms of fire protection. So this was our best bet. We have another video to show. So if you bear with me, gentlemen.
I really like the lights. I may borrow that idea.
All right, so again, we're going to do the same thing. The flow meter is to the right over here, and to the blenders in a section, then we're going to show the two visualizations. There we go. There you go.
You can really see the mixing there.
Yes. So that's what we're trying to accomplish. We're trying to bring the air in and make sure that the blender is able to, I'll use the word swirl the airflow so that it will mix the bulk of the air across the cross section of the duct system. So that shows that. Would you like to see that again, gentlemen?
Here it should be. Yes.
There we go.
Did the smoke generator leave any residue on the inside of the ductwork?
We noticed, no.
Now, all the orange bands are not orange and white when we were there.
Of course, the electrical smoke, I think, has an oily substance that's mixed with water, as I recall. I only know that because we spilled some at a church where they were using it, and it was a mess to mop it up.
Theatrical smoke is usually a glycerin and water mixture.
Okay, well, that explains the, it was slick. I didn't know if it was an oily substance or what, but glycerin makes sense.
Okay, gentlemen, so you see what we have accomplished. We have a test stand set up. I have a young man who wants to go to grad school for his master's, and we're going to use this to try and do a more thorough study where we're going to look at the equivalent length downstream of that blender where the irrotational flow goes away. That comes into play in terms of accurate pressure measurements. This is something Mark Pavot pointed out to us. We're going to take a look at what is the pressure drop across this blender. I would say this to you, that's one first question I would be asking. If I put a blender in a duct system, what's going to be the additional pressure drop, and can the existing fan handle that? What surprised me at the Hodges Library, they already had on their air handler units, there's 17 of them, 16 of those 17 had some type of a blender on the supply side that was already there. So in that aspect, it's just simply a matter of taking that blender out and putting this blender in. So that's a positive. The other is, I know that we're already retrofitting the campus with air ion generation. Where is the best place to be putting this? You can generate these air ions in the center of the duct and on the perimeter of the duct, but I'm not sure in a turbulent flow because there's a lot of issue, or I should say interaction between the momentum forces, the viscous forces, and the turbulence that you have. And in that instance, am I getting a good mixing across the complete duct section, especially if that duct is 3 foot or 4 foot in diameter, which is typically what you have in these large air handlers. So the use of a blender makes, to me, good logical sense. And the best place to put it is just downstream the air handler unit, so that you have upwards of 5 to 10 seconds of time where that air gets mixed very well before it goes out of the supply register. One thing to remember, that Reynolds number of 1 million, it goes down rapidly as we go down the tree to the various sections of the duct that go to various rooms and registers in the respective library. So that shows you what we've done. I want to congratulate my students. I think that they did a great job. I also want to thank Dr. Friels for his efforts in working with the students in terms of getting the CFD modeling, and Mark Pavot. I really appreciate the opportunity to work with you, and I want to continue that in a much broader sense, which we'll be talking about.
That sounds great to me, and I guess I want to echo that. Just great work to everyone. It's been great working with you, and obviously to all the students. I mean, this seems like a great capstone project to me, and looks like you all did a really, really good job. So thank you.
All right. So are there any last questions from anybody?
I would like to make one comment, Dr. Miller.
Jim?
We touched on it a little bit in those CFD analyses that were shown, but I wanted to emphasize how well this blender worked. I was really impressed with the pattern of swirl that got created. There was a clockwise and a counterclockwise component, and the mixing was just outstanding. I've never seen a device that worked like this. So, and I also want to talk, I tell Dr. Saval, thank you for pointing out the use of the realizable K-epsilon. It really made a difference in the results.
Great.
And it was more difficult to solve, but it really changed the results significantly.
Okay. No, good,
So,
good to hear.
thank you all. And the students did great. This is outstanding. And I really want to congratulate the whole team.
I have to say you did a good job on your presentation. I was impressed. Do have one question. If you injected the ions right before the air handling unit on the suction side of the air handling unit, would that give you the sufficient mixing? Or maybe you wouldn't have to have as a blender that would impact the airflow as much? Just a thought.
Well, I think I can handle that one.
Okay.
That was my first thought. Let's put it on the supply side where it really mixes. That's from the return side where it really mixes good. And that's where Blender Products would put their device where they're bringing in the outdoor air that is mixed with the return air. And what he wants to use that blender for is to get a good bulk temperature across the section of the duct, a well-mixed airflow. Well, if we put it there, Gary, the duct and the evaporator coil is wet because it's dehumidifying the air. And the ions would do a great job of cleaning the coil, but then they would be dissipated and no longer available for doing what we want to do.
Okay. I didn't think about the coil. Okay.
Yeah, I think the one other thing with that too, I mean, on some levels I like it. I think the other issue you have, right, is that the air handling unit is taking and it's recirculating some of the air, and it's also bringing in fresh outdoor air. And depending on the outdoor air temperature, it's changing that ratio to try to minimize the use of the heating and cooling coils, staying within, parameters for bringing in the correct amount of outdoor air. So depending on which, either the outdoor or return air you chose, I'm trying to think, I guess you'd be generating the same number of ions, but the actual flows would vary throughout the day and throughout the year in each one of those paths, and that may make it harder to control.
Okay, point well taken. All right, folks, it is 9:46. We've finished and well in time. Any last questions? Because we're going to say thank you for your attendance, and we will be talking to you in the near future.
Quick question, Bill. How easy was the ductwork to assemble with those snap lock type connections?
Super easy.
Glad to hear it.
And flange connection was great.
Wonderful.
Pearl connection, I should say. It worked
Good
out.
morning, everybody. I don't think I've met most people on here, but Dr. Miller, thank you for inviting me. I'm Charlie Waddell. I'm the actual founder and CTO at Global Plasma. We make some ionization systems. I think it was a great presentation. Great job, students, and I look forward to more research from your team. And also, if this video is available, I'd love to show some of my engineering department this stuff.
Yeah, same here.
Working it, and Charlie, good to hear from you again. You and I have talked in the past, and you're going to get it, okay?
Great.
Excellent. All right, with that, folks, I want to thank you for your attendance. I really do appreciate it. And I really appreciate having worked with these young guys. They did a great job. Made me look better than I am, which you are. And I wish them well in their careers. And for all you guys online, thank you for your time.
Yeah, and just, yeah, congratulations to all the about to graduate students.
Thank you.
Thank you.
All right, goodbye, everybody. Charlie Waddell, who just came on there, he's with
Is it
Global.
still being recorded?
I just ended it.
I think that's just.
It's
It's not.
Okay.
So we'll go back.
We were wrong. I did practitioners, but we were all over there.
Trying to talk slow.
No, I got halfway through that. I need to slow down.
Guys, did good. Excellent. So Charlie is the head of the global position, so he makes all these air ions. You know, he was willing to actually fund portions of this project. I'm talking about this project, I'm talking about a much larger grandiose scale project. We're gonna fully instrument. That's what I'm after. So, anyway, good deal. Keep in touch with me, okay?
Thank you.
All right. Good luck on your exam, which are coming up.
Oh, yeah, thank you. Yeah, we're gonna need that. Yeah, but that's the only one that I'm not confident in.
Hi, Dr. Mill.
Hi, Al.
Thank you. Thank you.